In the last section, we saw that we can work out the ratio of the reflected amplitude as compared to the incident amplitude for the wave as it hits the surface and gets bounced off and reflected. And we can do the same thing for the transmitted. But in the real world, we don't measure the amplitude of a particular wave, certainly not in the visible spectrum where it's oscillating at 10 to the 14, 10 to the 15 hertz. So we instead measure intensity. We measure not the amplitude, but the intensity. So rather than dealing with the reflection and the transmission coefficients, small r and small t, what's more useful to consider is the reflectance, capital R, and the transmittance, capital T. And we define these as being the ratio of the reflected intensity, the total reflected intensity, divided by the total incident intensity, and obviously the same measurement for the transmission. Now, the angle of incidence is equal to the angle of reflection for the reflected beam, and so it's just a nice simple ratio of IR over I sub I. The angle of transmission is not equal to the angle of incidence because of Snell's law, and so the transmission expression for transmission is a little bit more complicated, as we'll see in the diagram here. So we have our incident beam coming in. It hits the surface, and on the surface it has a projected area of capital A. Some of that light gets reflected at an angle of theta r, and some of it gets transmitted at an angle theta t. And so if we think about the total intensity within that volume, then we have some value A cos theta I, which is then incident on the area A. We have some of it being reflected, some of it being transmitted, and we assume that no light is lost via any other means. Now, for any wave, the intensity of the wave, or measure of the energy that it carries, is proportional to the amplitude squared. So the intensity for some light beam is proportional to its electric field squared. The constant of proportionality here is the speed of light in vacuum, c, times the permittivity of free space, epsilon naught, over 2. For the reflected beam, then we have to think about the speed of light in the reflected medium and the permittivity of the reflected medium, and the same for the incidence. We have to think about the speed of light in the incident material, the permittivity of the incident material. And so if we define our value for capital R, the reflectance, as the ratio of the reflected intensity over the instant intensity, then we just get a nice simple expression which says that it's the ratio of the squares of the amplitudes. In other words, capital R is related to small r, the reflection coefficient, with a nice simple relationship that capital R is equal to small r squared. And all of that's because the speed of light in the reflected and the incident material are the same, and the refractive index is the same as well. If we look at the light which is transmitted, so the light which hits the surface and goes from material 1 into material 2, or the incident material into the transmitting material, then we do the same process, only this time we have a more complicated expression. We can't cancel the permittivities or the refractive indices and the speeds in this case, and so we have to keep our expression here, which involves the refractive index of the incident material and the transmitted material. But again, you can see that there's a fairly straightforward relationship between capital T, the transmittance, and small t, the transmission coefficient. Now, for all the energy which flows into that cross-sectional area A in the diagram above, if it's not reflected, it must be transmitted. We're saying the light isn't lost by any other mechanism such as absorption and so on in the material. So the energy which goes into that surface area A must be the same amount of energy which leaves it, either by reflection or by transmission. And given this relationship, we can then express that in terms of the amplitudes, because we have Fresnel's equations in terms of the amplitudes. So it's nice and complicated in terms of the equations, but at least we have a set of equations. And we can gather together terms, cross out the similar terms, and rearrange everything so that we get the value for R and the value for T is equal to 100%. So in other words, energy is conserved across that interface. If we add together the reflectance and transmittance, then they come to 1. Whatever amount of energy we put in, that energy is conserved, and it's divided into either reflected or transmitted beams, or both. So relationships between the reflectance and the reflection coefficient for the different polarizations. We have the same relationships as we've seen above, only here we take into consideration the fact that the light is now polarized either parallel to the plane or perpendicular to the plane. And again, what we can do is we can plot out these curves as a function of input angle or incidence angle. And here we see for the perpendicular polarization that at all points the value of R plus the value of T is equal to 1. Okay, energy is conserved. And as we increase the angle of incidence, we get to a point where all of the light is being reflected, none of the light is being transmitted. And there's a point here, around about 80 something degrees, where half of the light is reflected and half of the light is transmitted. Okay. For the parallel polarization, we can do the same thing again. Remember, for the parallel polarization, we have Brewster's angle, and so Brewster's angle means that the amount of light which gets reflected is 0, and so the amount of light which gets transmitted is 100%. So we go through that Brewster's angle as we've seen before, and again, as we go to 90 degrees incident angle, 100% of the light gets reflected and none of it gets transmitted. We can also show that for the light which is broken down into a parallel and perpendicular component, that if we add together the parallel and the parallel reflected and transmitted components, again equal to 1, and the same for the perpendicular. So again, irrespective of what polarization the light has, the energy is always conserved across that interface. As we go to higher and higher incidence angles until we get to the point where the light is just coming straight down and being reflected off and back up in the direction it came from, then the value for the reflection and the specifically the parallel and perpendicular component is no longer defined. We can't remember the plane of incidence is the plane which contains the incident beam, the reflected beam, and the normal to that surface. If the normal and the incident beam and the reflected beam are all on one axis, then as it hits that surface, there is no single plane that defines the plane of incidence in that case. So our plane of incidence becomes undefined in that situation. And for that particular condition, we can simplify it because all the cos zeros and the sine of zeros, sines and cosines will be either 1 or 0. And so we can simplify the value for the reflectance, capital R, which will be, as I say, the same for parallel or perpendicular because it's undefined, that we have a nice simple expression, the refractive index in the transmitted medium minus the refractive index in the incident medium divided by refractive index in the transmitted medium plus the refractive index in the incident medium, all squared. That's a wee bit more messy for the transmitted beam because, again, we don't have cancellations because the refractive indices are different for the two beams, for the incident and the transmitted beam. If we look at an example now, if we take the case of just some straight, the refractive index of glass is about 1.5, and if we're going from air into glass, then the refractive index is 1, then the reflectance is about 0. In other words, at every interface, so if we have just a slab of glass and the light comes in at right angles, we're losing 4% because of a reflection there. It starts to travel through the glass, and again we're assuming there's no absorption, and then we lose another 4% there, and the light will then travel on through it. So we're getting 4% lost at every interface. Now, if you think about any kind of reasonably complicated optical system, there will be more than just two interfaces. There will be many interfaces in between elements of different refractive indices. And so if you had many surfaces, then you can imagine that quite quickly you're going to actually lose all of your light. If you're losing 4% at every interface, or a number like that, then you're going to end up with not very much light being reflected at all. In practice, what happens is that the surfaces of these materials are coated with what's called an anti-reflection coating. So it's a very thin layer of a dielectric material which reduces the amount of reflection that we see at that interface.